Let's move on to our next presentation. Continuing on the space science theme, here is Aaron Lott from the University Space Research Association, talking about the collaboration with HPC Research with NASA Ames. So this is a great back-to-back. Aaron, welcome. Thank you for joining us today.
Thanks. Can everybody see my slides okay?
I can see your slides perfectly.
Great. I was getting really worried after you wasn't able to get things set up there. All right. Well, thanks for having me. It's great that you guys were able to put me and Piyush together here, because I think building on a lot of what Piyush was just describing, part of the goal of USRA is to help in setting up collaborative research and staff for NASA in the HPC research and machine learning space. So we have a contract with NASA, the NAMS contract, and under that we do HPC research, but also a lot of machine learning research. Some of the projects that Piyush mentioned regarding the anomaly detection in the flight data, the exoplanets with the TESS and Kepler data, wildfire detection. These are the types of things that our researchers work on. And over the last year, we've been working with Piyush and the HPC division to help broaden collaborations within universities, with university researchers, but also with students, to help facilitate providing more capacity for HPC research at NASA Ames. And so I'll talk about three things today. One is our university-led high-performance computing research program with a couple applications that are being developed. These are kind of inspired use cases for HPC and trying to map out future architecture designs and requirements for driving these types of applications. Secondly, I'll give an overview of our HPC internship program and describe a couple of the internship projects that have been worked on over the last year. And then finally, I'll describe some work that we're doing with the Pacific Research Platform to help port NASA applications to PRP, to help engage with academic communities that are making use of that platform, but also to help to make use of that platform toward accelerating some of the development within academia to transfer that back over to NASA. So this is kind of the outline for today. So the first off is our HPC research program. We're really trying to target opportunities to have practical value of enhancing the NASA services within the next 2 to 5 year timeframe. And in that, there's a wide range of research areas that could be in scope there, and I'll describe that in the next slide. We're also looking toward increasing diversity, equity, inclusion, and building more capacity to serve the workforce in HPC research, as Piyush mentioned in the slide. You know, this is an area of need for NASA, and we're trying to help build educational programs and research programs to help move in that direction. So some of the areas that NASA are targeted for us to work with universities on is in frameworks and compute services, as well as HPC for AI and machine learning, which is kind of the focus of this workshop or conference there. And then also the data storage and retrieval services, and I think this has a nice carryover to machine learning. Is a lot of, IO is kind of a bottleneck for a lot of these types of algorithms and machine learning models. And then also software and applications to help improve ways to make things portable or more efficient. So these are the types of things that we're trying to support through our programs. Two of the projects that we have started this last year with the University of Utah through the PI Valerio Pascucci and also Sabode at Cal Poly Pomona through this research program. Basically, we have Piyush working on a lossy compression algorithm for data streaming or for visualization. And we have this project by Sabode where they're identifying flight control planning for UAV, multiple UAV operations and wildfire applications, but also applied to other applications as well. So I'll give a little bit of an overview of each of these. So in the project with Piyush, it's an interesting idea for helping with visualization, in that you can partition a compression algorithm to have kind of a two areas in which you can do compression. One is in the data resolution, and the other is in data precision. And based on how your application requires different trade-offs, you can still be able to perform, kind of like a high-end streaming of the physical simulations at a much lower rate. So you can see these visualizations. This is a data set that was almost a terabyte in size, and they were trying to look at some of the flow dynamics in that box. And then you can also look kind of these compressed comparisons, from around a gigabyte to just a few megabytes, being able to still provide, nice streaming service of data. One of the things that is being worked on right now in the project is to map this type of algorithm over toward exploring a coupled ocean atmosphere simulation with a very high degree of resolution, and being able to create a notebook environment to facilitate visualization of these simulations. So this is one of the projects that they're working to map these algorithms within a particular NASA application to enable high performance visualization in the NAS. The other application I mentioned was the HPC for flight control, planning, and multiple UAV operations. This is a project that is born out of the kind of the novel use case of having UAVs be deployed for a variety of applications, but the one that we're first targeting is fire detection and suppression services. So these UAVs can help ground crews identify where to put resources and how to plan those resources during the fighting of fires. This can also be used, for example, in precision agriculture, crop dusting applications. One of the constraints of UAVs is that they have very limited capacity to have a single payload. So you'll see on these UAVs, you might have one UAV doing monitoring or have some visualization devices, and another being used to actually deploy some sort of fire retardant or things of this nature. And you might not just have one camera, you might have a whole host of different information channels from different UAVs, and they have to work in concert. So making sure they don't run into each other, understanding how to effectively plan and control these, and being able to adjust for conditions that are changing dynamically in real time is there's a lot of computational problems associated with that. So what they're looking at doing is using the NAS system for you basically transmit the sensor data to NAS, and then you would be running a variety of algorithms to be able to direct the next steps in terms of what to do at the current waypoint or where to target the next waypoint and how to manage movement of the UAVs. And you can see here a whole host of different types of UAVs that would be helping in terms of combating a fire, or, for example, getting 3D reconstruction of LiDAR to back to ground crews to inform how to plan their movements. So this is the application in trying to deal with these large data streams in real time and linking it to the HPC and understanding how to set up the system as you scale the number of UAVs with different information channels to make this a viable real-time application. As I mentioned, there's many different components of this project, and a lot of what's been done thus far in our project is to get things set up with the application to start informing requirements of the underlying HPC components and start to make some changes or updates to the algorithm to leverage those resources effectively. One of the platforms we're making use of, and I alluded to this earlier, is the PRP, or Pacific Research Platform. The team has mapped various algorithms onto that as kind of a staging environment toward mapping this application over to the NAS. One of the nice things about PRP is some of the flexibility in setting up new libraries and dependencies. And once we kind of get a stable setup there, then the idea is how do we then map that over to NAS effectively, and what are some of the changes that we'll need to make there in order to allow NAS to have a service for working with control centers operating UAVs for these types of dynamic applications. Okay, so those are the two kind of research projects that are university-led research in HPC that we've been facilitating over the last year. We also have an active HPC research program. We've worked with folks from both undergrad and grad students in our internship program, and we are currently doing things remotely, but there's potential to also, I think, in the future be back on site relatively soon. And so we're hoping to have opportunities for students to be able to work with researchers at NASA on HPC projects in the areas, kind of like what Piyush was mentioning before, to help both have an impact in the NASA applications at present, but also help train the workforce so that we're able to create a pipeline of talent that's able to serve the NASA missions. Two of the projects that we've worked on over the past year are both on HPC. One is in exploring HPC I/O capabilities for machine learning use cases, and the other is building containers for HPC and machine learning workflows on the NAS. And so I want to just describe a little bit about each of these projects. For the HPC I/O capabilities for machine learning, as we've been talking about in this conference, data-driven machine learning applications and high-performance computing is a growing area. And there are certainly various bottlenecks that are different in the machine learning use cases than, say, a traditional physics-based simulation. And I/O is certainly one of the demanding features that we have to address. And there's different challenges of how to understand the effective I/O in the machine learning use case on HPC. So this study was to try to evaluate I/O performance of a variety of data-driven machine learning use cases and be able to kind of break down where some of the pain points are within the NAS for supporting these different applications. So we evaluated three machine learning applications, and then trying to assess the patterns of data movement within each of them. And then from those patterns, we then tried to profile workloads on the NAS using IOR as a benchmarking tool. So the three applications we had, and these are also different phases of machine learning that we looked at. So the one was we were training an anomaly detection algorithm, looking at early flight data in commercial flights to try to detect whether there's an anomaly in different parts of the systems on the aircraft. And so this is a convolutional neural network coupled inside a variational autoencoder doing supervised learning. And there's basically two different steps that we evaluated. One was the pre-processing of the data to be able to get everything into a format for training, and the other was the actual training of the algorithm. The second application was using a linear regression model for establishing wildfire perimeters and being able to assess various risk estimates based off of both satellite and lightning strike data. And this was a statistical linear regression model as opposed to, say, a like a convolutional neural network machine learning model. And we looked at both the pre-processing and the training aspects of that model in terms of performance. And then finally, we had a deep convolutional neural network that we're using for flood detection based off of satellite remote sensing data. And we were also using this, once we trained that model, we evaluated performing inference using that model on the remote sensing data. So in each case, we used Darshan, which is a comprehensive application for IO profiling out of Argonne. There were some limits to how well Darshan worked with Python and TensorFlow. That was one of the things we identified in the project, was that would help us provide more granularity in terms of the specific studies we were able to then set up for IOR to then characterize the IO performance and timings. So once we ran Darshan kind of to get an average estimates of the workflows for each of these different stages for the three models, we ran IOR to be able to characterize performance. And so we have a little table describing for each use case what the bottlenecks were. And so for the flight anomaly detection, we had fairly small IO sizes in the data preparation. The data volume was greater than memory, but we only had to read it once. And then in the flight data, we also were, when we were doing the training, the IO sizes were fairly large, but the data volume was less than memory, and we had to call that many times during the training process. So here, the idea is that if you have multiple ingesting of the data during the training, you want to try to reuse that in memory if you can to improve performance. Similar in the flooding use case. Now in the wildfire use case, there we're looking at a statistical model. So we basically just have to loop through the data the one time, and it's a statistical, dependency on the regression model. And so that then has a computational dependent aspect of the overall IO is not as much of a factor. Whereas in the flooding case, this was a much larger data set. But we were able to basically say that so long as the as long as the velocity of the data was such that we could set things up in memory, we were able to get good performance of this model. So this is just a slide outlining some of the IOR results that we had for the different workflows that were kind of established from Darshan. And what we found was that if you had a single full data set read, that would exhibit an IO bottleneck. But if you had multiple data set reads, you could basically take advantage of memory if you partition things well. When you're performing inference, you might get an IO bottleneck if the data is large enough compared to the, based on the velocity of the data. And then one of the things that we were also examining was how to set up the file system on the NAS to provide the best performance over the transaction sizes that were common within each of these models. And essentially, as you would probably expect, you want to turn off the luster straping because this was essentially a feature that's used to help maintain performance across multiple processors. Whereas these were really single processor type jobs running over each of the data sets. As I mentioned also, the incompatibilities of Darshan with both the Python multiprocessing and the TensorFlow data limited some of the data the types of data movement that we might want to model when establishing a signature for doing benchmarking using IOR. And that was kind of one of the key takeaways from this. Is I think that would be a great area for the communities if Darshan would have better support for that integration. So that the next project we had is dealing with containers for HPC and machine learning workflows. And the idea here is that essentially we want to provide more portable tools for the university community, but also within NASA for, between systems, and, being able to map NASA applications into university clusters for novel exploration of methods. Research would be useful, but also going back the other way, being able to take ideas from universities and map it back into the NAS would be a useful tool as well. Helping to reduce those barriers is kind of the idea here. Where we're building on is the E4S stack out of DOE and trying to map that over to the NAS machines. So as I mentioned, the main idea here is we want to be able to move things over to various large-scale computing systems. And I think also, the inverse arrow is also appropriate here. So again, we use the E4S project to build a custom image and deploy that to the NAS systems. And our intern, who's a Stanford student of Steve's, helped optimize all the policies to be able to run and deploy it on the NAS system. And for supporting HPC workflows or in a set of tools on NAS, we were able to do some benchmarking using the OSU benchmark on MPI. And he was able to get all the message passing interface working with Singularity and Podman, and be able to mimic the same latency performance and roughly the same bandwidth performance as without any containers. So this was met with great excitement within the HPC team. And we're looking toward doing some more work with this to support machine learning workflows. And specifically, we're looking at, for each phase, because I kind of alluded to this in the project in terms of the IOR, there's different requirements and there's different tools that are used in machine learning models at each stage of the training, learning, data preparation process. So we're basically making some custom images to be high performance for each of these stages, and then finally to be able to serve up the models on the NAS. So that's kind of the context for this student project. And finally, I wanted to talk a little bit about this work that we're doing with the Pacific Research Platform. And this is a large set of universities, over 50 research universities take part in doing research using this kind of Kubernetes cluster. And we wanted to be able to set up some of the services that are based on NASA products to be able to engage with university researchers on the PRP. So one of the ones that we're setting up right now is called the Digital Earth Geospatial Visualization Service. And I'll talk a little bit now about what PRP has for those of you who aren't familiar, so that you can kind of get a sense for how this might serve as a bridge to engage with universities in terms of, as a staging environment or a test bed for exploring things going into NASA. So as I mentioned before, PRP's Nautilus system is a hypercluster. It utilizes Kubernetes for managing and scaling the containers, and it uses Rook for the data services. And as I mentioned, it has over 50 universities as a part of this. And I guess to be a member of it, as far as we are, USRA is a member of it. We have a Fiona node that has several GPUs in it. and people contribute resources to the cluster, and people are able to make use of these various systems as an individual group, or also leveraging the resources of others when they're not being used. So it's a great tool for supporting academic research. Here's some specifications of the data transfer nodes. These are very high performance, up to 100 gigabits per second data transfers. They also have systems that have up to 8 GPUs or FPGA boards, and 256 terabytes of disk space. There's also, like I said, the field programmable arrays. This is an area in which the NASA systems don't yet support this in the NAS, and being able to identify some of the areas in which these advanced architectures could be leveraged for given target NASA applications. This provides a way in which to do some exploration of testing and analysis. And finally, being able to support rapid cluster management and development of codes that isn't as static, provides a lot of flexibility in supporting an active software development, algorithm development group. So this is a well-managed cluster in that regard that definitely facilitates collaborative work and fast-paced work within research teams. So one of the things that we've done is set up this Digital Earth Geospatial Data Visualization Service using the PRP. The little visualization here on the right is of the service. This was basically looking at the NorCal fires from 2020, and also the lightning strike data. So in the light blue, you'll see we're taking into account satellite data around where the fire perimeters are, and also the dark blue is where there were lightning fire strikes. And this is being used for some of the machine learning models to help in terms of future wildfire detection and planning activities for disasters. This product's also being used by the Pomona team as they're looking at using it with their UAVs for helping to understand some of the data that they're assembling and being able to put that data back into the framework. This is based on NASA's Whirlwind software development kit. So this is a NASA product that helps bring in all the data. And then it's also being used by the Civil Air Patrol for helping to estimate where there could be flooding risks post-wildfire. And finally, we're looking at integration of Digital Earth with the NASA Data Reasoning Fabric, which is an air mobility marketplace that allows for multiple like UAVs, things like this, to be able to interface with these geospatial data. This is a little bit of the stack. We've been building this together with interns from Foothill College in the Bay Area. I think that's right over near Stanford, similar area. So anyway, we have a team of several researchers, students working from the Science and Learning Institute there, helping us build this up. We also have one other USRA project where we've been doing some exploration with the Black Marble product suite from NASA. This is a product suite that's used for evaluating the night sky and being able to look for. I remember there were being some nice pictures at the beginning of COVID showing, how things were just kind of dark more than before. People were less moving around. It captured some of that information. So this application has been mapped over to the PRP to help do some new code development of some of the underlying models for analysis and inference. So with that, I'll give you back some time. And if you have any questions, you have any students that would like to work with us, please feel free to reach out to me. Thank you.